It's great. Oh.
Yeah,
All right.
So yes, we're all gonna take it for granted that this is gonna be a good talk, and it will. This will be about factorization. I present to you Grant Moles, and we'll tell us all about it.
All right, so let's go ahead and start off with is this, okay, it's there. Start off with a familiar context. Let's talk about Z, a set of integers. So we're talking about the set of integers. We have this really nice property that I'm sure you're all familiar with, which is that every n in Z, every integer other than -1, 0, and 1, for reasons we'll get to in a second, factors uniquely into a product of primes. So we've got our primes 2, 3, 5, 7, so on and so forth. 12 is 2 squared times 3. 63 is 3 squared times 7, so on and so forth. Every number that we pick, we can factor uniquely into a product of prime numbers. So the idea behind this talk is, where does this property, this really nice property, carry over into? Does it carry over everywhere? Well, we're gonna see that in a second, but I think right now it's going to help to talk about what I mean by a context, where we're working. So we're going to go over some really quick terminology, just to kind of give everyone a feel for what we're talking about. So first of all is a ring. Think of ring as the context we're working with. So it's a set with addition, multiplication, and some nice properties. Roughly speaking, those properties are going to be associativity. So addition has the associative property, multiplication has the associative property. Commutativity, in general, for a general ring, we only require that addition is commutative, but for everything we're going to be talking about today, multiplication is also going to be commutative. So it doesn't matter what order you add or multiply things in, it's going to be the same result either way. We've got identity. So we've got 0 is the additive identity. 1 is the multiplicative identity. Again, in a general ring, we don't actually require that multiplication has an identity, but for everything we're going to be talking about today, we are going to have 1 in our ring. We've got distribution. So multiplication, if we multiply across a sum, we can do that same thing, except multiply by each element of the sum and then add them together. And right. We have additive inverses. So we have additive inverses, which basically means we have negatives of all of our numbers. We're not actually going to require that we have multiplicative inverses, because if we do require that we have multiplicative inverses, everything just gets kind of boring, and so we're not going to require that. And this is what we're going to be working with a ring. All of the rings that we're going to be talking about today have an additional property that is going to make them what we call an integral domain, which seems like a complicated word, but really all this means is no non-zero elements multiply together to get. So we can't multiply 3 and 5 together and expect that 0 is going to come out of that. If we're going to get 0 out of a product, one of those things are better than 0. So The idea that this is an integral domain should be suggestive that these are going to resemble the integers. You may notice that the integers have all of these properties. Addition and multiplication are associative and commutative. We have 0, we have 1. Multiplication distributes over addition. We have negatives, and we have we can't multiply two integers together and get 0. You may also notice that the integers do not have multiplicative differences. So just to kind of get a feel for what these rings look like, let's take a look at a couple of examples. So the integers, as we already said, the integers are integral domains. And as we have already said, these the integers have this nice property where everything factors uniquely into products and primes. I guess a couple other definitions that I want to put up here real quick are, can everyone see if I write in this space? Probably not. I'll move it over here. So a couple other things are units and irreducibles. Because if we get into some of these crazy looking rings, it's not going to be enough to just talk about prime numbers. We're going to have some sense of what it means to be irreducible. So with a unit, this is actually a pretty simple concept. A unit is an element with a multiplicative inverse. So we said we're not requiring everything to have a multiplicative inverse, but if it does, that's this special kind of a unit. Irreducible, on the other hand, is a non-zero, non-unit. So it's not the additive identity. It's not one of these elements with a multiplicative inverse, such that it can't be written as a product of non-units, which is all just a fancy way of saying we can't break it down any further. Think about primes in the integers. With a prime number, you can't split it up into two factors unless one of those factors is 1 or -1, which are our units. So, like I said, Z is an integral domain. So it's got all of those features over there. And as I said before, the units, what are our units in Z going to be? Things that we can multiply and get 1. Right. Units are just plus or minus 1. Because we don't have any fractions in the integers, nothing else can be multiplied by and get 1 as a result. And the irreducibles are the primes. In general, it's actually not going to be the case that prime and irreducible mean the same thing. And that's beyond the scope of what we're talking about today. But in the case of the integers, the irreducible, the set of elements that we can't factor into other irreducibles are just the primes. We'll take look at a couple more ways. The reals and the rationals. So these are going to be integral domains. They have all of these properties. We can't multiply any two real numbers or two rational numbers together to get 0. So these are integral domains. And what are the units?
Everything.
Everything except 0.
Yeah.
Everything. Everything. But 0 is never going to be a unit. You're never going to multiply 0 by something and get 1. So yes, everything is a unit except for 0. These are special types of rings called fields, and they're really nice. If you're working in certain concepts, you've ever worked with linear algebra, you've talked about vector spaces, which are defined over fields. The thing about fields, though, in the case of factorization, is that they're really boring. There's nothing fun happening in fields because irreducibles don't exist. In the definition of an irreducible, we're talking about non-zero, non-unit elements. Except in a field, everything is either zero or a unit, which means that we can't even talk about factorization. Nothing fun happens in a field. So let's talk about some things that aren't fields, but aren't the integers. Some of you may not be familiar with this notation, but it is something that you are familiar with. This is the set of things that look like this. AI integers, and n is a natural number. It's just a ring of polynomials. Polynomials that have coefficients in the integers. So again, we're working over something interesting because we don't have everything being a unit. What would the units here?
A0, the over the higher term of 0 is with A0.
Yeah. So all of these higher terms, we can't have any. If we multiply two polynomials together, we know that the degrees are going to add up. So if any of these are non-zero, we're going to have something that's not zero in a higher degree term, and one doesn't have any higher degree terms. So we're going to need just a zero, and specifically, we're going to need to be plus or minus 1 again. Because any prime number, again, we still don't have fractions. And the irreducibles, they're going to look like a lot of different things. I can't put a nice closed form description of an irreducible in this set, except that a lot of you may already be familiar with what irreducibles look like in this, because the irreducibles are going to be prime numbers. All of those prime numbers are still going to not factor into anything. If they did, they would have to still just be integers. And we know that we can't factor a prime into integer. And this is a really almost circular definition here. Irreducible polynomials. Polynomials that cannot factor down, which is a very lazy thing to write up there, but that's the closest I'm gonna get. I could spend all day listing irreducible polynomials that look like a lot of different things. And in a very similar manner, we can talk about QX, the polynomials, except now the coefficients are allowed to be any rational number. Both of these are still going to be integral domains. They still have all of these nice properties. They sort of inherit them from Z and Q respectively, except now that it looks a little bit different. The units are now Q, but still not 0. We can still only invert rational numbers, but now we can invert every constant polynomial. Anything that doesn't have any higher terms, we can still multiply by something, the reciprocal, and get 1, unless that thing is 0. And I'm not even going to write it this time because it doesn't seem to be worth writing. The irreducibles, we don't have primes because primes don't really exist in the rationals. Well, we still do just have irreducible polynomials. Kind of a lazy thing to write again, but it's true. So this is kind of getting a feel for what we're working with. And all of these rings, these integral domains we're talking about, see trivially here, the polynomials over D and Q, all of these are going to have unique factorization. If we're ever talking about an integer, we know we can factor in the primes. Any polynomial, we can factor into irreducible parts. We can work with a degree argument there. But what does it really mean to have unique factorization? Well, I'm going to write up the definition. Let's see. This seems like a good place for it. Yeah, this is a good place for it. So let's say R is an integral domain. Such that, and now we're just going to write up a bunch of things that collectively mean we have unique factorization. So the first one is going to be every element every non-zero, non-unit element, that is, will factor into a product of irreducibles. So far, we're not requiring that factorization to be unique. We're just saying it can be written as a product of irreducibles. Of course, we're excluding zero and units here because if we're talking about zero, we don't want to be able to multiply two things together and get zero unless one of those things is already zero. And with units, the units are going to throw everything off. So we're kind of throwing those out the window. Two. If we have two factorizations, so we have a product of things on the left, we've got a product of things on the right, and they're equal to each other. With all of the pi's and tau's being irreducible. So these are all irreducible. Then we're going to require that they're of the same length. So again, so far we're not requiring that these factorizations are unique. We're just saying if we do have two factorizations, they should be of the same length. The same number of irreducibles should go into building the product, no matter how we decide to do that. And finally, this is where our uniqueness is going to come in. If we do have two products of irreducibles, now note that they're of the same length, n, then each I is a unit multiple of some tau. So something on the left here, we don't, anything we pick over here, any of these irreducibles, it should be a unit multiple of something. Now, why didn't I say it has to be one of the things? Why am I allowing that unit multiple thing to happen? Let's take a look at Z as an example. And let's say I'm talking about 6. Well, 6 is a pretty easy thing to factor. We can factor this into 2 times 3, right? Pretty straightforward. But did you know, fun fact, 6 is also -2 times -3. Oh, crazy stuff. So the idea here is that there's a lot of stuff we could pull here if we want to be smart about it, you know, be sarcastic, pull a bunch of stuff out here. But these are basically the same factorization. They just have a -1, a unit multiplied into. So that's why we need that unit multiple caveat in there. Okay, well, I talked about unique factorization domains. We're just going to skip right past that. Just ignore that for a while because I don't want to talk about that anymore. So I'm just going to take a sharp left. We're not going to return to that ever. We're going to talk about Fermat's last theorem. We will get back to that eventually. So Fermat's last theorem, this famous theorem, Fermat back in what, the 1500s, is that right? 1600s. He wrote in the margins of a textbook that he had a proof that there are no non-trivial solutions to this for n greater than or equal to 3. We know that there are solutions for n equals 2. Those are Pythagorean theorem, are 3 sides of a triangle. For n equals 3 has no non-trivial solutions. A lot of the times, mathematicians like to throw in things like that, non-trivial. For the same reason we throw in unit multiples over here, it's because sometimes people like to get smart about things, and I could plug in all zeros here. I could plug in 0, 1, and 1 here. Those are the kind of trivial solutions we're talking. Something in there should not be 0. So, no non-trivial solutions. He wrote this in the margins of a textbook. And he said, I have a great solution for it. And then he died. And for a long time, people looked at that and said, well, what was his solution? Let's try to figure it out. People now have probably agreed that he probably did not have a solution. He was the ultimate mathematical troll. But a lot of people did have a lot of thoughts about this. How can we solve this problem? And one of the first things that they figured out was, well, we don't need to figure out this for general. We can focus just on the primes. Because let's say that P is a prime that divides n. Let's say that P n is P times A. Well, then we can split this up and say that if this has a solution, then this is a solution for the same problem, but for P. So if we show that it has no solutions for primes, then we don't even have to worry about just general things. So another thing that people look at, well, we can split this into cases. Notice that if all of these things share a common factor, we can factor that factor out until they don't have a common factor. So we can also assume that the GCD of all of these things is 1. And finally, people said, well, let's say we have a prime that divides 2 of these things. Well, if it divides this, and it divides this, pull it out front, it also divides that. So we can again reduce that. So there are 2 cases to consider here. One where the given prime here, the prime that we're interested in, divides one of these terms, and another case where the prime divides none of the terms. We're going to focus on the case where prime doesn't divide any of the terms because it's easier to explain. So this sat unsolved for a long time until 1993, when a man called Andrew Wiles came along and proved it, became super famous, and used elliptic curves, which was not something that Fermat would have known about, which is why people think that he probably didn't have a solution. But did you know that Andrew Wiles was not the first person to prove this, and it was actually proven in 1847? Someone came along and proved it. They didn't actually prove it. We'll talk about that. So somebody came along and said, well, this is a prime, right? We can actually factor this if we look in a ring, in fact, an integral domain, not the integers. So we can factor this as z to the p equals x plus y times x plus y omega times x plus y omega squared x plus y omega to the p minus 1, where omega is a pth root of 1 in the complex numbers. So it's a root of x to the p minus 1 equals 0. That's not the trivial one where x is. So we can factor this in this way. Now we get into a lot of weeds here, and I'm going to skip over some of the details because I don't have time to explain all of the details. But it turns out that everything on the right side here has to be relatively prime. And what I mean by relatively prime from each other is that there's no irreducible element in the ring z adjoint omega, which is just the integers. We're going to throw this root in there, and then whatever comes up in sums or products, we're going to also throw in. What this is going to end up looking like is this. Yeah. So it's integer linear combinations of powers of omega, actually out to p minus 2. It turns out that p minus 1 is actually a linear combination of all of the others. If you look at the irreducible polynomial that omega satisfies, but we can factor it in this way. Now, what we can tell is suppose that pi divides x plus y, where this is going to be some irreducible. This is some irreducible element that divides. It divides this, and it also divides, if we assume that it also divides x plus y omega to the k for some integer k, one of those other things, k not being 1 in this case. Well, it turned out that this is impossible. We cannot have this, and the reasons for that I could explain if you gave me like an hour or so. That's my total time, so I'm not going to do that. So we cannot have this, which means that whenever we break this down into irreducibles, the irreducibles that are here aren't in any of these other places. Well, let's think about that for a second. We've got irreducibles, and let's think about breaking both sides into irreducibles. Okay. So if an irreducible appears here, divide that, then I think you should agree with me that it also is going to divide this. So irreducible divides z to the p. Well, then it would make sense that that irreducible should divide z. So let's say that pi divides x plus y omega. Well, then pi divides z to the p, which means that actually pi divides c, and so actually pi to the p divides z. So we've actually got at least some multiple of p factors of this pi on this side. Well, then that should appear on this side, right? But we already said that there aren't any of those in any of these other places, so they've all got to be in here. Which means that in fact, x plus y omega is a p power. Alpha to the p, maybe with a unit. We're going to allow there to be a unit. So again, a lot of reasons that I don't have time to explain here. But it turns out that if this is true, then x has to be congruent to y mod p. What that means is that p is going to divide the difference of this. P divides x minus. So if these things are congruent mod p, that's all well and good. But hold on a second, let me just rearrange some things here. I'm going to subtract this across, and I'm going to subtract that across. Everybody agree that that is the same equation that I just wrote up there, just in a little bit different form, since p is an odd number? Well, if that's true, then actually that should be true as well, right? C and X at negative Z should also be congruent on P. We'll check out this trick. So we can write this equation, X to the P plus Y to the P equals Z to the P. Well, mod P, these are the same thing. So this is actually 2x to the P. But over here, this is negative x to the P. Mod P. So if we add this across, 3x to the P is congruent to 0 mod P, which means that P divides 3x to the P. Well, this is where another case comes in. People said, okay, well, if P is equal to 3, we can check that case individually. It turns out that there are no solutions for P equals. Let's just make that quick change. Now we're assuming that P is not only odd, it's also greater than 3. So P divides 3x. Well, but we know P doesn't divide. So actually, P divides x to the P, which means that P divides x. But we assumed in this original case, P doesn't divide any of x, y, or z, which brings us to a contradiction. So in this proof in 1847, we have proven Fermat's last theorem. We have proven in some special cases, other cases require other proofs, but we've proven it. Except we haven't. Because we assumed these things. We assumed that this was a unique factorization number. That took me a while to write up then. So I'm only going to call them UFDs from now on because it's shorter to write. We assumed that that was a UFD. In that, we said, well, we've got a factor here, we've got an irreducible factor here, which means that it must appear on the other side. And once it appeared on the other side, we also said P of them are here, which means there must be P of them over here. But if we're not in a unique factorization domain, we might not have this case. Irreducibles on the left don't necessarily need to appear on the right. So if any of those were not UFDs, the proof failed. And that's why it took another 150 years to prove Fermat's last theorem, because it turns out that some of these are not UFDs. Unique factorization doesn't always hold, which is a crazy thing to think about. Every context that we've worked with, coming up through school, we've had unique factorization, or we've had multiplicative inverses that make everything boring, but we still have unique factorization. It's just kind of trivial. But there are places where unique factorization doesn't hold. And let's take a look at some examples of where unique factorization fails. We're going to get back to Fermat's last. Yes. So if any of you have ever seen a ring in which unique factorization fails, probably the first example you've seen is this. It's going to be very similar to that notation over there. The polynomial notation should be suggestive that we should be working with integers times powers of square root of -5. But we really only have to go out to here because if we throw in square root of 5 squared, that's an integer again. So we can just absorb it into that first. So it turns out that unique factorization fails. Well, let's take a look. 6. We've already talked about how to factor 6. We know that 6 is 2 times 3. Well, the integers are still here. So 6 does still factor as 2 times 3. And it turns out that in cases like this, where we're adding more elements, it's not enough to say these are prime numbers and therefore they are irreducible. Sometimes prime numbers will factor in these cases. In this case, they don't. These are still irreducible elements. For today, since I only have a little bit more time, you're gonna have to take my word on it that these are still irreducibles. I could explain it to you if you wanted. It would take a second. But it's not the only way to factor 6. As it turns out, 6 is also 1 plus the square root of -5 times 1 minus the square root of -5. If we multiply these out, we know that x plus y times x minus y is just x squared minus y squared. So this is 1 minus square root of -5 squared, which is 1 plus 5, which is indeed 6. So 6 factors 2 different ways. Now, the caveat here is returning back to this thing that I underlined. We have to make sure that nothing over here is a unit multiple of anything over here, because these could be the same factorization. They could just look very different. They're not the same factorization. We should note that if they were, then either 1 plus square root of -5/2 or 1 minus square root of -5/2 would have to be here, and they're not. So these are indeed different factorizations. It turns out that this first thing holds. Every element here will factor into irreducibles. We can find irreducibles, factor everything into irreducibles. And in fact, case 2 holds as well. If we factor anything into irreducibles one way and factor anything into irreducibles another way, they're still going to have to be the same length. You'll note that there are 2 irreducibles over here, 2 irreducibles over here. They're the same length, and that actually holds for every element from here. That's what's called a half factorial domain, or an HFE, which isn't important to what we're talking about today. I just wanted to write this up here because this is what I do my research in, is half factorial domains. So I wanted to share that. So if 1 and 2 hold, we're talking about a half factorial domain, but this doesn't hold. We've seen that we have 2 equal length factorizations, but they are not unit multiples of each other. So surely this is as weird as it gets, right? This is as weird as factorization could possibly be. We can factor things, but they're not the same. Well, actually, no. Now we could show an example of something where 1 holds, where everything factors into irreducibles. But we might get different length things. Those things do exist. They're called atomic domains. But I think it's more fun to show something where we can't even factor things into irreducibles, because those places are wild contexts to work in. And sometimes, like mathematicians like to do, you gotta kind of be a smart aleck about it. So let's say that the ring we're working in is the ring of polynomials over Q, except we're gonna throw in a twist. Basically, what this means is that the polynomials that we're talking about can be any polynomial with coefficients in Q, except that we're requiring that a constant term has to be an integer. So this would be something like 5 plus 1/2 x plus 356 over 3x squared. Had to make sure that that didn't reduce. But yeah, this is an element here, but this is not. We have to make sure that those constant terms are integers. So how can it be that elements don't break down into irreducibles? Surely we've got to come up with some wild term here with x to the 147 plus x to the 13 minus 5/6, something crazy. It's just x. X does not factor into irreducibles. Well, let's assume for a second that we didn't know. Let's assume for a second that we thought, well, maybe there are some irreducible elements out there that we could multiply together to get x. And let's call those alpha 1, 2, alpha. So we factored it into irreducibles. Well, let's think about what these look like. What's the degree of the polynomial x? Yeah, 1. Yeah, the degree of the polynomial x is just 1. So as we know, if we multiply together polynomials, the degrees add together, right? A 3rd degree polynomial times a 5th degree polynomial gives us an 8th degree polynomial. So what can we say about the polynomial, the degrees of those polynomials? Yeah, we've got to have n numbers that add together to be 1, which kind of gives us a boring case that this is degree 0, this is degree 0, and let's assume that this last one is the one of biggest degree. So one of these things is linear, and the rest of them are all integers. Well, another thing that we know about the integers is that it's an integral domain. We can't multiply things together and get 0. So if alpha n is ax plus b, and we multiply all of these other things that are just integers, then we've got alpha 1, alpha 2, alpha n minus 1, alpha 1, alpha 2, alpha n minus 1. And if we multiply these together, we should get x, right? Which means that this linear term is 0. Except that if the linear term is 0 and it's a product of all of these things, one of them has to be 0. These are all irreducibles, which means they can't be 0. So b has to be 0. So actually, alpha is just some rational number times x. But this is not irreducible. And this is where being a smart aleck is going to come in handy here, because I can factor this into two things that aren't units. This is 2 times 1/2 ax. Well, that's certainly not a unit. It's got degree 1. We can't multiply a degree 1 polynomial by anything and get a degree 0 polynomial. So this can't be. And 2 is not a unit, because the polynomial ring, we're requiring that all of those constant coefficients are integers, which means that 1/2 is not in here. So actually, this is not an irreducible, which means that no matter how we factor x, we can't get a product of irreducibles. So actually, in this context, we don't even get condition 1, let alone the other two. So this unique factorization idea, it's something that in everything that we're used to working in, it holds. In these integers, in, well, R and Q, which are boring, in the polynomial rings over Q and the polynomial rings over Z, unique factorization holds. But it doesn't in some cases here. And let's show that. I've been attacked. So, can anyone tell me, some of the grad students out there, what p-value am I going to pick? What prime number am I going to write out of the word? For what? For a place where this UFD condition fits. One of the grad students made. This everybody has a subset there. Anyone know it? Dr. Going on?
23 probably.
Yeah.
You'd also use 37, 59, or 67.
Yeah. So it turns out that this UFD condition actually will hold as long as P is less than 23. But when P is 23, we get this crazy condition. And let me write something on the board here. One plus omega squared plus omega to the fourth. Here, again, omega is a 23rd root of unity. Multiply it by itself 23 times, you get 1. Plus omega to the fifth, plus omega to the sixth, plus omega to the 10, plus omega to the 11. Multiply by 1 plus omega to 5, plus omega to 6, plus omega to 7, plus omega to 9, plus omega to 11. I ran out of room because those are long things to write. It turns out, if you multiply these things together, their product is divisible by 2. 2 divides both of those things. But because all of our elements are looking like this, 2 doesn't divide either one of those things. So 2 in this case is actually an irreducible that divides neither thing here. But if we factor it into irreducibles over here in a different way, 2 is going to appear in irreducible factorization on this side, but not on that side. We don't have unique factorization, which means that unfortunately, people in 1847 are going to have to figure out how to live another 150 years to wait for Andrew Wiles to prove Fermat's last theorem before any of that's going to come back into the Well, that's all I've got. Thanks all for listening.
Any questions? I have one. The product there, how did you come up with those elements?
There was a problem in a book that I read.
Oh, really?
And it turned, if you multiply these out together, and you keep in mind that 1 plus omega squared plus omega to 22 is 0. If you keep that in mind, multiply these out, and you'll find that all of your coefficients are 2. Or I think there's one that has 4. But either way, it's divisible by 2, and neither of those things.
Yeah, it's interesting that because even though this proof doesn't work for small values, it eliminates an enormous number of things, right? In fact, I think they adjusted this a little bit and got the regular prime, right? So that got more of them.
Yeah, this is the proof that failed, led to a more general proof that also failed, but kind of generalized things, and led to the creation of algebraic number theory, which is the field that I like to work in.
Well, I think
Thank
actually
you, failures.
that's right. I mean, actually, that's a great point, because in mathematics, a lot of good math comes out of people's failed attempts at trying to solve something else. It's really interesting though, because I think, now you might be able to correct me on it if I'm wrong on this, but they define these kind of primes called regular primes, and it generalized this. And so when you they proved Fermat's last theorem for regular primes, and so that picked up 23 that doesn't work, and it picks up all the primes less than 100 except those 3 I named, I think. And of course now Fermat's last theorem solved without doing regular primes. But of course, mathematicians are always curious and they want to know, how many regular primes there are. But the status of that right now is, of course, for primes either regular or irregular, it is known that there are infinitely many irregular primes, but it's not known if there's infinitely many regular primes. So that is definitely a case of a premature definition. So anyway, any other questions?
So in that corner, you write in 1847, why did you only check the irreducibility of the term you marked with rectangle x plus y? Yeah. Is that anything well report?
So the reason that we're working with specifically this term is just because it's the nicest term to work with. It's easier to show that this is relatively prime from everything else here. And the proof that this holds is easier to prove for that term in particular. I believe you can prove it for any of the terms, but I haven't done that. And I think it's a little bit.
Okay, any other questions?
I think maybe for your next trick, you should get a seminar on how to get so much on board. Still be able to use the board. It's actually quite impressive.
Let's give them a thanks, yeah.
So I'll make